I want to start with a geometric vector review. We've already worked with a few vectors in a plane. They can be used to represent the motion of an object in one or two dimensions when they're confined to a plane. Vectors have both magnitude and direction, and they can be represented symbolically in several different ways. They can be represented as the specification for a line segment that is directed with the arrow over the top. So for example, PQ with this arrow on the top would tell me that a vector starts at the point P and ends at the point Q. When I construct that geometrically, it looks like a ray with a beginning point at P and the arrow at Q. It can be represented in angular brackets as A, B. In a Cartesian plane, this will look like a ray that starts at the origin and ends at the point specified by the ordered pair AB. But if the brackets are angled, it tells me it is specifically a vector, whereas the ordered pair is just the point at the tip of the vector. You can think about a vector as a directed distance away from some beginning position. Another notation for it will be AI hat plus BJ hat. Sometimes they'll just say AI plus BJ. I or I hat represents what we call a unit vector, a vector of unit length 1 in the horizontal direction, and J or J hat, a vector of unit length 1 in the vertical direction. So that on a coordinate plane, my AI hat plus BJ hat vector will look like a ray that starts at the origin and ends at the ordered pair AB, where I go out A times one unit vector in X and go up or down by B times one unit vector in Y. Finally, I can represent it as a bold-faced lower or uppercase letter, or a lower or uppercase letter with an arrow over the top. Some texts reserve the lowercase letters to represent unit vectors, and others use them interchangeably. If you're writing these out, it's hard to do a boldface, so I find it easiest to use the designation of my letter with an arrow over the top. Again, if I construct this vector, my U, or U with the arrow over it, or my V with an arrow over the top of it, just looks like a ray that has a beginning point at the base of the ray, and it has a specific length and a specific direction. Two vectors U and V are said to be equal if they have the same magnitude and the same direction. Any physical phenomena that involve magnitude, which is length, and direction can be represented by vectors. Some examples might be electric fields, velocities, or paths of moving objects that we typically call trajectories. Quantities such as mass, temperature, or price all have magnitude, but they don't have any direction. These are known as scalar quantities. There is one vector that has no direction, and we call it the zero vector. We designate it by 0 in bold-faced or 0 with an arrow over the top. It has a magnitude of 0 and no direction. We define this because it makes it convenient for constructing a complete set of rules for vector operations. I can do a lot of things with vectors once I have them defined. I can multiply it by a scalar. Scalar multiplication involves simply multiplying a vector by a scalar quantity. If my scalar quantity is C and my vector is V, then scalar multiplication simply gives me C times the vector V. The value of C times the vector V is called a scalar multiple of V. The magnitude of C times the vector V is given by the magnitude of C times the magnitude of the vector V. Keep in mind, magnitude will always be positive. The negative signs attached to my vectors indicate direction. If C is greater than 0, then C times the vector V will have the same direction as the vector V itself. But if C is less than 0, then C times the vector V is going to be in the opposite direction from V itself, and it will be parallel to V. If C is equal to 0, then C times the vector V gives me the 0 vector, and two vectors that are scalar multiples of each other will always be parallel vectors. So for example, if I have a vector that's 2 times the vector V, and here's my vector V, notice that they have different lengths but the same direction. Whereas -3 times the vector V is also parallel to V, but it points in the opposite direction. Now, since 0 times the vector v is a scalar multiple of a vector with no direction, it is going to be parallel to every vector I can ever construct. I can also add vectors geometrically. Graphically, I do this using something called a triangle rule or a parallelogram rule. Use whatever makes the most sense for you. Here are my two vectors, u and v, and I want to add them together. I'm going to add u plus v. By the triangle rule, I'm going to place the tail of the vector v at the head of the vector u. This will look like my red u vector going up to the right, and then the tail of the v vector starts at the tip of the u vector and goes further up to the right. Then I'm going to construct a resultant that goes from the tail of my first vector u to the tip of my second vector v. This resultant gives me the sum of u plus v geometrically. If I use the parallelogram rule, I connect the vector u and the vector v at their tails to form two sides of a parallelogram. And then I sketch in the other two sides of this parallelogram and then construct a resultant that forms the diagonal of the parallelogram beginning at the vertex where my vector u and vector v are joined. This diagonal is my resultant, which is the sum of u plus v. I can also subtract vectors geometrically. I subtract them by the triangle rule and by a more direct route. So again, I have u and v as my vectors, and I want to find the difference, u minus v. By the triangle rule, I'm going to place the tails of u and v together. Then I'm going to construct a vector that is parallel to v but in the opposite direction and have it start at the tip of u. So I'm going to construct the opposite direction of v, negative v, and then I'm going to construct a resultant from the vertex of the two original vectors, the u and v vertex, to the tip of the minus v vector to get the vector u minus v. This is a little convoluted. There is a more direct route for subtraction of vectors. I'm going to place the tails of u and v together, just like I did for the triangle rule, and then I'm simply going to construct a resultant that goes from v to u. There is u minus v. Notice that u minus v in this direct route is exactly equal to u minus v in the triangle rule. It's just a little bit shorter way of getting there. So let's work some examples. I want to write the following vectors as sums of scalar multiples of a unit vector w in the horizontal direction and a unit vector v in the vertical direction. I have already plotted one of each of the unit vectors with their own origin on the grid here. The first vector I'm going to look at is a vector that starts at O and goes to P. Then I'm going to look at a vector that goes from O to Q and another vector that goes from Q to R. Notice that O to P is going to be a vector that starts at the origin point where my unit vectors are set up and ends at P up and to the right. OQ is going to start at the origin of my two unit vectors and go down to the right to point Q, and the point QR starts at Q and goes up to the right to end at R. So for OP, the first thing I want to do is put in the vector I'm interested in. I'll sketch the vector starting at the origin and ending at P. And then I'm going to see how many quantities of the unit vector W I need to proceed horizontally before I construct quantities of the unit vector V going vertically. I need 2 unit vectors of W to the right, and then I'm going to go 1, 2, 3 unit vectors of the unit vector V upward to end at P. This means that the vector OP can be written as 2 times the unit vector W plus 3 times the unit vector V. For the vector that starts at O and ends at Q, I first sketch in my vector. It starts at the origin and drops down to the right to end at Q. Now I'm going to see how many of the unit vector W's I need to move horizontally, and then how many of the unit vector V's I need to move vertically. I need 1, 2, 3 unit vectors of W to the right, and I need 1 unit vector downward to end up at Q. This tells me that my vector OQ will be given by 3 times the unit vector W minus the unit vector V. For the vector that goes between Q and R, I first construct the vector. I start at Q and end at R. Now I need to see how many of the unit vector W's I need and how many of the unit vector V's I need to move from Q to R. I need one of the unit vector W's to move to the right horizontally, and I need 1, 2, 3 of the unit vector V's to move upward vertically to end up at R, so that my vector QR is also given by the unit vector W plus 3 times the unit vector V. So now you get to try it. Pause the video and write each vector as a scalar multiple of U and V. When you're ready, restart the video to check your understanding. U and V are unit vectors. U is a unit vector vertically and V is a unit vector horizontally. The first vector we want to work with is the vector that goes from O to the point P up and to the right from the origin. The second vector extends from O to R, which is up and to the left of the point O. And the third vector is PR, that goes from the point P back to the left and up to the point R. For the vector OP, I first construct the vector I'm interested in. It starts at the origin and goes up to the right to end at P. I need 2 unit vectors of V horizontally to the right and 2 unit vectors of U vertically upward to end up at P, so that my vector OP can be written as 2 times the unit vector V plus 2 times the unit vector U. For the vector OR, I draw in the vector starting at the origin and ending at R, which is up and to the left from the origin. Now I want to see how many horizontal unit vectors I need and how many vertical unit vectors I need. I need 2 unit vectors to the left horizontally and 3 unit vectors upwards to arrive at the point R. My vector OR can be written as -2 times the unit vector V plus 3 times the unit vector U. For the vector PR, I construct my vector that starts at P and goes up to the left to end at R. I need to move 4 unit vector V's to the left and 1 unit vector U upward to arrive at R. This means that my vector PR can be written as -4 times the unit vector V plus the unit vector U. This is a really quick review of vectors presented geometrically. Let me know if you have any questions.